Okay, so while we set up for the next speaker, let's try this again. The title of the presentation is Improving Object Grasping Through Synthetic Perception-Based Post-Correction in Robotic Manipulation. And the speaker is Guillermo Trinidad Barnech from Universidad de la República, Uruguay. Yes. So the floor is yours.
Okay, thank you very much for that introduction and for everyone from me here. As he said, my name is Guillermo Trinidad, and I come from Uruguay, and I'm going to be presenting my work about improving object grasping through synthetic perception-based post-correction in robotic manipulation. So it's quite the long title, so I'll try to explain it step by step, right? So first of all, I'm going to say what the task is, or what we are talking about when we say robotic manipulation in object grasping. There's a lot of tasks to test this. In our case, we are talking about this robot, which we call Guayabo. Has an Open Manipulator Pro equipped with a Cell Mini mounted on the wrist. That's a stereo camera, for those who know. And we are trying to grasp these 5 very different objects from these 20 positions marked as red dots in the image. So that's the task we are trying to solve in this case. And for that, we first implemented a baseline grasping pipeline, for which we first use OMDET, for object detection. This is a very popular or somewhat popular open vocabulary object detection pipeline. So we first detect the object, and then we use SAM from Meta to get a mask of that object. And combining that information with the depth perception, we can have like this point cloud representation of the object in space. And then we use this simple alpha shapes algorithm and some filtering and also some clustering to build, in a sense, a very rough a mesh of the object, right? So we're trying here to build a 3D model of the object as we go, because we have no prior information about the object, right? So with that, we have what we need to try to grasp it, right? So we first use this baseline implementation where we only go for the middle of the object. So this was a video, but as you know, we have some trouble here. And you can't see it, but the performance of this pipeline is not perfect, of course, but it's quite good in the sense that it's grasping almost 50% of the objects. Oh, so we do have the video. Sorry, it was autoplay on my computer, right? So you can see from the numbers, it's not that good. But if you watch closely, we are here measuring success rate. So if it has to pick the object and bring it back, so if it falls or whatever, we are saying that's not good enough. So for the ball, for example, just a few millimeters of error, you can't pick it, right? Or for the can, the same thing, because it's very heavy. So this is not a bad pipeline inherently, but small errors cause big mistakes, right? So now we're going to the improving part, and I'm trying to tell you about our background. So in our work, in our previous work, we've been focusing on intuitive physics as mental simulation in the sense of Tomer Ullman's and Joshua Tenenbaum's work, where people in their careers, or robots in our case, have this fully blown mental simulation, like a fully physics engine in their minds, and they try to test hypotheses there, and they try to, in most of the case, or in more classical work, try to predict if a tower block is going to fall, if 2 objects are going to collide, or some things like that. So in previous mental simulation work, we've been playing around these ideas of how this mental simulation that's equipped with physics and collisions and things like that can inform what I perceive. And we've been playing around with this tension between perception and simulation, and mental simulation, and when you choose one and choose the other. So we've been like toying around that. But recently, there's been some studies that say that mental simulation, or in this case, like intuitive physics, also guides some other processes. In our case, we're interested in the evidence about visual tracking, right? So now, I'm going to talk about synthetic perception and what we say that, what we mean, right? So, as I said, and now you understand, this object model that we built is now put into the mental simulation of the robot in the place we initially guessed it is, right, based on the point cloud and the stuff. So now what we do is we try to render an expected visual stimuli for the robot, right? Inside the simulation, we have the object and we have the robot model, and we know where the cameras are supposed to be. So we can use it as a forward model that tries to build a visual expectation of the scene, right? So where am I supposed to be seeing this object I'm trying to grasp? And that takes the forms of a bounding box, right? So we are abstracting quite much. So why we do that? Because now we have this expected visual stimuli that we can compare with the real or the perceived stimuli, and that gives us an error signal, a mismatch between these two bounding boxes that we feed into a very simple inverse model in this case that uses like the centers of these bounding boxes and the sizes of these bounding boxes and tries to compute a delta position vector to correct the object position. So that's the synthetic perception based pose correction. So we are trying to correct the object pose by using this synthetic perception. So that looks like this. So time is going to the right, of course, and we see that initially the object has a really big mismatch. And if you look, it's not quite obvious, but the object in the simulation is moving like further from the robot and a little bit to the left, and at the end of these 3 steps, we have a match between these 2 bounding boxes, right? So this is like the fully blown architecture. We can go into detail if you want, but I'm already getting the cards, so I'm going to pass. And then we implemented 3 models, right? The first one is the one I already talked about, the baseline, where we just see the object, build it in a simulation, and just try to grasp it as it is. Then we use an always-on correction, which starts the motion towards the object and tries to update the object position at full speed, right? This is 30 Hertz for those who care. And at 4 evenly timed intervals during the trajectory, we update the arm goal position, right? So we are correcting the pose all the time, and at some points we just say, okay, the object changed position, so I changed my goal. And then in the other hand, we implemented a motion-aware correction that only means that the robot is going to perform the corrections only when it's not moving. So what it does, we also change the behavior of the reach, where we place the object in the simulation, and of course we perform this first correction, then we try to grasp it as it is, but we stop at 80%, like this 80-20 spacely. So at 80% of the trajectory, it stops for a second, that triggers another correction, and then goes for the final reach. And I had to play these things. So here we have the continuous approach, this always-on variant, when you can see like the motion is quite smooth, and we'll see in a minute that it performs quite well. It does, for the ball, for example, it's very precise, it's working quite good, but from some other objects, it's not that good. And the motion aware, you are going to be seeing very clearly how this performs that 80-20, right? So it goes and then goes for a little more, and this is just for you to get a grasp on how this looks. And these are the results, where we can see that it's divided by object, and on the far right we can see like the average performance of all these things. So the first thing we are seeing is that using the correction always yields better results. That's quite expected, but it's always good to see, right? And the thing that was quite puzzling or quite interesting is that the best approach is this motion-aware approach, where it stops and then like does this 80-20 split, and that yields a result of like 92% success rate, which is almost the double from the baseline. So we're hoping this is like, it's not the state of the art, of course, because it's a simple task, but it's quite the improvement, right? So just to end, and I think I'm good on time, I would like to thank my supervisors, Juan Valle-Lisboa and Gonzalo Tejera, and also Bruno Lara, who is recently working with us, and we are looking into future directions and working with him. So with that said, if you have any questions, we can discuss that.
Thank you very much. Any questions? I see one there.
Yeah, thanks. It's quite interesting. Have you kind of tried moving the dots in different configurations to know if, say, it's optimized for learning this particular grasping positions, or if it's more generally able to change its motion trajectory?
Well, the thing is, the robot that is not learning and it's not aware of these specific positions. In fact, the positions are chosen to be like spread across the range of motion of the robot. So I will think new positions won't change the results because they are not baked in any way. They are marked in the image because I had to place the objects like to repeat the experiment, right? But the robot has no knowledge about either the positions or the shape of the objects or something like that, and it's not learning. So I would assume it's not like overfitting to the scene or something like that.
Okay, thanks.
You're welcome.
Thank you. We have a question from the back.
Hello. Thanks for the nice work and the presentation. I've got a question regarding the update. Do you just update the pose, or do you also fully update the reconstruction of the object model? And a second question is, why do you think this motion-aware approach is better than the continuous? Is there like some motion blur in the continuous approach that inhibits its performance, or what is your reasoning there?
Yeah, well, that's those are really two great questions, and I'm quite intertwined between them because we are not updating the model. We think we should be updating the model because what we think is a problem with the continuous approach is that during the trajectory, the robot observes the object from new points of view, right? And since we are not updating the shape and we are using the bounding boxes, we think that the mismatch might be regarding the new perspective and not just an error on the post estimation. So we do think that's one of the issues we have right now with the continuous approach. And on the other hand, for the last part, I don't think it's motion blur the problem. I think it's a more like synchronization issue where we render the synthetic perception, and once we compare that with the real perception, those are not really, like, we didn't do any specific work in order to synchronize that in a more sophisticated way. So I think that is playing a role also. But yeah, definitely we should be looking into those things. Thank you.
Okay, any maybe last quick question over there while the next speaker can start to set up. Down there. Thank you.
Yeah, I was wondering, from a more bioplausible perspective, it's just an imaginary, so don't worry about the question. But so we don't re-render the object in our imagination, right? And correct for millimeters. No, I know that this is a very robotics way to go. So my question will be, is not better to correct for the trajectory of the end effector towards the error on the position of the object than actually the object position itself? So where your hand is with respect to the object?
Yeah, well, that's actually a great question, and we are currently working with Bruno on that kind of stuff where this error signal, in a way, or this mismatch between expectation and perception is solved by movement and not by correcting my internal model. In this work, not this work, in my work, we were focusing more on this idea of like, okay, suppose we have this mental simulation, and since we thought that this visual tracking thing, of course, you're not fully rendering, but there is some top-down information flowing in that direction. So it's just like the most simple way to implement this model correction through error. But we are looking right now into sensory motor learning and trying to build this expectation by sensory motor experience. And in that sense, the movement plays a bigger role in the correction of the trajectory. Yeah.
Okay, thank you very much. Let's thank the speaker again.